I'm going to run through a simple diffraction gratings exam question, and I hope that this will be of some use for you if you are attempting any other kind of diffraction gratings question, such as the one I give you for homework. So this is from 2009, question 27. What you have is a laser producing a narrow beam of monochromatic light. Monochromatic, obviously that's one of these words that you should know the meaning of, a single wavelength. So part A, it says red light from a laser passes through the grating as shown, and what you have is the grating just here, and you have the angle theta, which I should be able to zoom in on. So that's theta there, which is the angle between the central maximum and the maximum that you're interested in. Okay, so in this case, in this question, it's the second order maximum. So A is basically quite a straightforward question. A series of maxima and minima is observed. Explain in terms of waves how a minimum is produced. So bread and butter, easy warm-up question. And if you don't know how to answer this, it's in your notes. You should learn it. This is below the marking instructions from the SQA. So they accept that if you say the waves meet out of phase, then that's fine. Or if you say a crest meets a trough, that's fine. Or if you say that the path difference is n plus a half times lambda, then that is also fine. So the crucial thing here is you must talk about the waves meeting or combining. Okay, so meet. Part B. The laser is now replaced by a second laser which emits blue light. Explain why the observed maxima are now closer together. Okay, again, this should be pretty straightforward. So this is with red light. Your maxima are like that. With blue light, they're telling you that the maxima are going to be closer together. Okay, so why is that? And like I said to you before, the equation is your friend, and the SQA agree, so they've got the standard equation, which is now m lambda equals d sine theta. So you could rearrange that to give you sine theta equals m lambda over d. So what that shows you is that the sine of this angle theta is proportional to the wavelength of the light that's coming through. So the wavelength of blue light is shorter than the wavelength of red light. And just to say that and to show this equation is enough to give you the mark. However, if you want to be completely clear, you'd say the wavelength of blue light is shorter than the wavelength of red light. And because sine theta equals m lambda over d, this means that sine theta is going to be smaller for blue light, so theta is going to be smaller, so the maxima are going to be closer together. Part C says the wavelength of the blue light from the second laser is 4.73 times 10 to the minus 7 meters, and the spacing between the lines on the grating is 2 times 10 to the minus 6 meters. Calculate the angle between the central maximum and the second order maximum. So this is an easy question, okay? They've given you the value for D. You don't even have to work that out. And they've given you the wavelength. So essentially all you're doing is substituting into the equation. So you write the equation as it's written in the datasheet. M lambda equals d sine theta. This is the second order maximum, so m is 2. Lambda is 4.73 times 10 to the minus 7 meters. D, the slit separation is 2 times 10 to the minus 6. And then sine theta is what you're trying to work out. And then when you inverse sine theta, you'll find that theta is 28.2 degrees. Nice and easy.